Suppose you find the successfully found the fixed point, and then your next interest is like, is this fixed point stable? The stable here means that for a we respect those fixed points. Suppose you have a small perturbations applied, and are you gonna return back to your fixed point or not? That's the concept for the stability. So the next step for the Poincare section for in response to those small deviation, as far as those deviation for the next point is closer to the initial perturbation delta x, you will end up reaching to the fixed point. So that's what we call the locally stable status. So suppose this is, let's examine in a pictorial with the figures. So suppose this is a limit cycle and this is a fixed point. So if you start with the fixed point, you're going back to its the initial point. But if you have a deviation from the fixed point, what will happen? So your deviation ended up reaching to the limit cycle anyway. That's the stable case. And suppose that your xk deviation a little bit further from the fixed point is not directly coming back to the limit cycle by one step, but still have reached to the point where in a Poincare section closer to the original deviation of xk, like this. So this is xk plus 1 less than or smaller than the x of k. That means as time goes by, if you just keep repeating this, you will end up reaching to the fixed point. That's what locally stable case is. So here again, the Poincare section for the limit side, the rimless wheel is like maybe your x of k is the Poincare section is the collection for the initial state. So if your x of k is your initial condition for your choice, the Poincare section could be calculated by solving single stance phase and the collision, so that your next step's initial condition will be minus alpha and eta omega minus, right? So that's the collection of xk, xk plus 1, xk plus 2 will be a Poincare section. So as far as this one is same as x of k, then you found the fixed point. So for unstable limit cycles, like for any deviation away from the fixed point, will never return to the limit cycle. So for example, if we have a kth x delta x of k deviation and start making another one cycle, so next Poincare section point, corresponding points will be farther from the fixed point as, of the x of k. That means you will never return to the limit cycle. That's unstable. So once when we obtain the fixed point, that's a kind of concept explanation. How can we check stability? To make the long story short, you just have to find out the eigenvalues of Jacobian. Okay, so for the Poincare section, you will find the fixed point and define the function g of x as the difference between your next steps f of x from the fixed point. Okay, and that's what we defined as g of x, and find the Jacobian of g of x star, the fixed point, and its eigenvalues, the Floquet multiplier, that will determine the stability. Why? That's what I'm going to explain. Okay, suppose you have a initial guess x of k, and that will give you the next initial point for the rimless wheel, x of k plus 1. Just keep running, that will actually reach to the fixed point. This is one example for the Poincare section. And let's define delta k x of k is the deviation of your kth initial guess from the fixed point x star. Okay, so that's how you define the deviation. And then for your next value, xk plus 1, the deviation of that value from the fixed point is now defined as delta xk plus 1. Okay, so that's the function of g, which is original fixed point and the deviated function input, and minus the fixed point. Okay, so you can actually calculate the delta xk plus 2 is going to be g of x star plus delta xk plus 1, etc. Now, With this function definition, let's apply the Taylor series expansion. Okay, xk plus 1, delta xk plus 1 is going to be gx star plus delta xk. That's going to be approximated as g of x star plus g prime, the first derivative of x of star, multiplied by the deviation. Okay, since g of x hat, the fixed is going to be 0 at fixed point by definition here. And note that this delta x should be small enough so that your Taylor series expansion approximation will hold. And this term is Jacobian of g of x hat, x star, sorry. Okay, so your next step's deviation amount will be a function of first step's deviation multiplied by the Jacobian. Okay, and since you want your next step's deviation will be smaller than the previous step's deviation, what that means is as far as your Jacobian norm is going to be less than 1, then you will be stable, right? So suppose Jacobian is sometimes like a matrix, like 2 by 2 or 2 by 3. It's not necessarily the square matrix. So suppose this Jacobian is given like this, and can you make a decision, is this stable or not? That's what I'm going to explain in the next slide. So suppose your next step's deviation amount is going to be a function of a previous step's deviation multiplied by the Jacobian. So if the Jacobian is very simple, like a diagonal term, you can easily say that your next step's value will be scaled down as half or 1/10 so that it will quickly converge to the fixed point. Okay, your deviation will reduce quickly with the amount of 0.5 and 0.1. However, if your Jacobian has a cross term like this, the full matrix, it's not really like intuitively give us the idea is going to be converging or diverging. Like it looks like all smaller than 1, so maybe converging. But let's try some examples. Like for deviation of 0.1, 1, 1, 2, 2, 1, what would happen for that Jacobian matrix multiplication? So each point multiplied by the Jacobian has been reduced to move to this black dot. So seems like it's getting, toward the origin, so maybe converging. But if you apply those Jacobian term multiplication again, okay, this value definitely looks like toward the origin, but this one actually passed through the origin and have a negative value. And this one seems like, moving this way, so maybe diverging. So if you're looking at those changes for the sequential change for the initial perturbation in x and y or x1 or x2 coordinate, sometimes not easy, especially where your J matrix has a full matrix, the cross term. Okay. So here comes in the eigenvalue problem. So eigenvalue problem by definition is AX equals to lambda x, and we are supposed to find what's going to be the x. Okay? What's going to be the lambda and what's going to be corresponding x, which is eigenvector. So what this means is you have a vector, you have a multiplication for the matrix, but the result will be your scaling. Like a lambda is a scalar value, so your vector is going to be multiplied by some number, like a 3 or 0.5 or something. So eigenvalues is a scale factor of self, I would say. Okay? So with respect to the eigenvalue, we can find the eigenvector that will satisfy this equation, which means if you are coming in one value, you can just scale by yourself. So suppose this axis is corresponding to eigenvalue 0.04, and this axis is corresponding to eigenvector 0.1, 0.1, means whatever in this axis will be scaled down by 0.4. So this has been reduced by more than half, and this one has been reduced by more than half. But in this axis, whatever you have a value here, okay, so you will be increasing by the amount of 1.1, And this value, starting from this value, will be increased by 1.1. Okay, as you keep multiplying those matrix, it's self-scaled at a factor of 1.1. So by viewing those point changes in view of eigenvector coordinate, it's a lot easier to predict what's going to happen because it's scaled up by this eigenvector corresponding to each axis. Okay, so eigenvectors are the axis of new coordinate system where those variables are decoupled and then scaled by a scalar factor. So coming back to the original eigenvalue problem, you have a jx is going to be lambda x and find out what's going to be the lambda, and corresponding solution for x here is going to be eigenvector. So if I wrote as eigenvector as v1 and v2 a column vector, you have a j v1 is going to be lambda 1 v1 by definition, and j v2 is going to be lambda 2 v2. So if you multiply by the eigenvector matrix to the Jacobian, which is multiplication of v1 v2 vector matrix, that's going to be j v1 and j v2. And by definition, it's going to be lambda 1 v1 and lambda 2 v2. And that's going to be formulated as an eigenvector matrix multiplied by the diagonal term of eigenvalue, sorry. Okay, so from this this value, you have a jv is going to be v lambda diagonal term, and then if you multiply by the v inverse on the right hand side, your Jacobian can be split as v lambda diagonal term and v inverse, I would say. So that's the decomposition. Okay, so the decoupled using the eigenvalue diagonalized vector. So coming back to the original, like a stability derivation, like your next steps deviations are a function of previous steps deviation multiplied with the Jacobian. So let's apply those eigenvalue decomposition for the j. So j is decomposed by v lambda diagonal and v inverse. So if you plug that in, you will have a delta x k plus 1 is going to be v lambda, v inverse, and delta x of k. And suppose this one is a coordinate transform. Okay, so you have a input of x, and you just multiply vector that will define a new set of state vector as z. It's coordinate transformation. So if you multiply by v inverse and left-hand side again, so this has been canceled, what you can get is a delta z k plus 1, like coordinate transformed deviation value is going to be previous deviation, coordinate transformed deviation delta z of k multiplied by diagonalized lambda. So you can easily tell are this going to be either getting larger or smaller depending on the lambda value by comparing the lambda value if the lambda value is less or greater than 1. Okay, so as far as your eigenvalues are smaller than 1, you're locally stable because your deviation coordinate transformed deviation will decrease over time. So again, by checking the eigenvalues of Jacobian, as far as those eigenvalues are less than 1, your system is locally stable. Okay, so these are the topic that I'd like to deliver at the solution method part. So we learned how we can simulate the walking. So walking has two solution steps, like a single support and double support, because double support is a collision solution. So you should solve using the momentum impulse relationship. And you should find the periodic gate using the limit cycle and fixed point, and even check if your found fixed point is stable or not by checking the eigenvalues. And later, I would recommend you to do the parameter study of your model to either check your model is feasible and your prediction from the model can explain the human behavior. And thank you for listening. And then for the next video, we are going to study about a bipedal inverted pendulum model. Thank you for listening.